So we're writing electron configurations, shortened electron configurations. Sometimes I call it noble gas. Some people call it noble gas configuration, and orbital diagrams. So we are writing ground state electron configurations. So these are configurations where the electrons are all in as low an energy orbital as they can be. So this relates to the Aufbau principle, or the building up principle. This is not a person. So the building up principle says if electrons are going to go around a nucleus, they are going to fill up the lowest energy orbitals before going to higher energy orbitals. So sometimes you forget like which orbitals are lower energy, which sublevels are lower energy. And so if you do forget, you can just write the numbers and along with the sublevels, and then you can start drawing these diagonal arrows. So like 1s is the lowest energy sublevel, and you fill that up before you move on, and when you move on you go to the 2s. This is a little bit weird, but I've seen some kids draw it on tests and it helps them remember. So we go 1s and we fill that, and that holds 2 electrons, and then we fill 2s and that holds 2 electrons, and then we go here and we fill the 2p and that holds 6 electrons, and then we fill the 3s, 2 electrons, and we keep going, 3p, then 4s, like that, 3d, 4p, 5s. So we have to fill it in that order. We fill up the 3d and then we fill the 4p and then the 5s. And so sometimes these numbers are out of order, but not the energy of the orbitals within the sublevel. So 4d has lower energy than 5p, has lower energy than 6s. That might make sense. But then what sounds a little weird is that 4f has more energy, or 4f orbitals, electrons in 4f orbitals, have more energy than 6s electrons. We go here, and we go here, and actually 7p is going to take us to the end of the periodic table, or element 118, so we don't need all the rest of these. I wrote them to point out that the 5th energy level does have 5 sublevels. We just never talk about 5G. We don't have any elements that have electrons in a 5G sublevel. Same thing for 6. 6 has 6 sublevels, but none of them, those don't get any electrons for any ground state atoms. And then same thing, we'll get rid of these. So those exist, those are places that electrons can be, but ground state atoms don't have them, or ions don't have them. So we're only going through there. All right, let's start with this. Practice this. I've got some atoms and ions here, and what I'd recommend that you do is get used to looking at the atomic number. So nitrogen, atomic number is 7. So you write that in the correct position. That's how many electrons it'll have if it's neutral, and it is. So we have 7 electrons. Now we're going to write the electron configuration, and we're going to fill in this order. So 1s2 gets filled. There's 4 of your electrons, and there's only 3 left. So there's your full electron configuration. Your noble gas configuration is going to, what we do, maybe that zoomed, I don't know. So we have nitrogen here, and for the noble gas configuration we go to the previous noble gas, which is helium, and we write that. Okay, so helium, the noble gas prior to this element is helium. We write that in brackets, and that takes care of however many electrons it has, and then we just write the electrons that are filled after it. So that's, we'll keep practicing. And then we need an orbital diagram for the last 2 sublevels. That'd be 2s and 2p. 2s is filled, 2p. We have 3 electrons. You should spread them out, and they should have the same spin. This is Hund's rule. Hund's rule. Look it up. Hund's rule. Look it up. There's 2 parts. Those electrons, when you put them in, you should spread them out. Right? Within a sublevel, they should be single as long as they can, and then they should all have the same, any unpaired electrons should have the same spin. So look that up. So those are 3 things for nitrogen. Now we get to phosphorus. Phosphorus's atomic number is 15. And so it has 15 electrons, except it has a 3- charge, so it should have 18 electrons. Full configuration, 2, 4, 6, that's a total of 10, 12, 18. So okay, so these numbers you might call them an exponent, or they're not exponents, right? Don't say 1s squared. Say 1s2, 1s2, 2s2, 2p6, 3s2, 3p6. Those should all add up to your total number of electrons. So you can check to see that you've done it right. Then we're going to do the noble gas configuration. The noble gas prior to phosphorus is neon. And that has 10 electrons. Okay, so writing this neon takes care of 10 electrons. And then we've got +2 + 6. That's 18, which is the 18 we wanted. So this is a quick way to check that you have the right number of electrons. And now we need orbital diagrams for the last 2 sublevels. And everything's full. A note, we have, for our, hope that zoomed. We've got 2 columns to the left. Those are known as the S block. We've got 6 columns, 13 through 18, to the right. That's called your P block. You've got 10 columns, groups 3 through 12. That's your D block. And down here, the lanthanides and actinides, there's 14 columns. That's your F block, right? 14 electrons fit in the F sublevel, and you've got 14 columns here. So we've got 10 electrons that can fit in a D sublevel, and you've got 10 columns right in the middle, so that's your D block. So what that means is for any of these atoms, if you know which block it's in, you know where the last electrons are going to be written. And we notice nitrogen and phosphorus, they're in the same family. They're both in group 15, but they're in the P block. So we expect that they are going to, especially if they're neutral, that the last electrons that we see are going to be P electrons, and we see that for nitrogen, right? 2p3. The phosphorus is a phosphide ion, so it has an extra 3, but we still see a 3p, right? We see these P electrons. Next one is lead. Lead is element 82, so it's 82 electrons. That's a lot. That's a lot. Lead is also in the P block, so I'm going to expect that my last electrons are going to be P electrons. It's really long, a lot of electrons. We know that it should be an even number. We have an even number of electrons. You can go ahead and add that up and make sure that you see that I've done it correctly. But there's your full configuration for lead. Noble gas configuration is going to be much more convenient to write, and so it's going to start with xenon. And that takes care of 54 electrons, and that's a lot easier to add than all the rest of this. Okay, so that would be our configuration. Now, something that you want to do with this, when you write an electron configuration that has this 4f and 5d in between the energy level 6 electrons, what you want to do is you want to take this 6s and scoot it over here next to the 6p. So do that. So this looks a little better, and what's going to happen is when electrons are going to come off of lead atoms, they're actually going to come from the 6th energy level first, and you can kind of see that lead forms a +2 ion, and lead also forms a +4 ion. Those are the only ions that we observe. And when you look at the electron configuration, you can see why, right? So we see that 2 electrons are in a 6s sublevel and 2 electrons are in a 6p sublevel. So it almost makes sense to say, okay, those 2 can come out and it would be a +2 ion, or these 4 electrons would come out and that would be a +4 ion. So anyway, just when you write these, it's a good idea to rewrite that so that you remember when you remove electrons, you remove them from the 6th energy level first. We'll do orbital diagram. Again, we got 6s and 6p. If I asked you to draw this and you drew 5d and 6p, that'd be fine. But there we have. Make sure you have them unpaired in 6p. Next is Pb4+, and I just did that so that you would see which electrons are removed. So we have 82 minus the 4 electrons, so we should have 78. And the ones that we're going to get, I'm not going to redraw that whole thing. The ones we're getting rid of are the 6p and the 6s. And you can double check the numbers. We've got 78 electrons that we need. Xenon is your 54, plus 14 is 68, plus 10 is 78. So always count your electrons, make